Hey everyone, when you think about motion, you probably think about how fast something is going, right? Like the speed of a car. But in physics, there's a whole other side to the story. It turns out which way you're going is just as important as how fast. To really get a handle on motion, we need to talk about both, so let's dive in.
All right, let's start with a little puzzle to get your brain working. Picture this. A cross-country runner just finished a grueling 10,000-meter race. They crossed the finish line, which is in the exact same spot as the starting line. Now, here's the question. What is their total displacement? They've obviously run a long way, but what's their displacement? Just hang on to that thought for a few minutes. We're going to come right back to it.
So, to figure out that runner problem, we first have to get one really fundamental idea straight. In physics, pretty much every quantity you can measure, from temperature to speed to force, can be sorted into one of two simple categories. And understanding the difference between these two is, honestly, the key to everything else we're going to talk about. Okay, so here they are, scalars and vectors. A scalar is super simple. It's just a number. It tells you how much of something there is. Like it's 72 degrees outside. Or you've been watching this for 50 seconds. It's just a magnitude. But a vector gives you more information. It has a magnitude, the how much part, but it also crucially has a direction. It answers both questions, how much and which way.
You know, the easiest way to think about a vector is to just picture an arrow. It's perfect, right? The length of the arrow tells you its magnitude, a longer arrow means a bigger magnitude, and of course the arrowhead points you in the direction. So that one simple arrow gives you both pieces of information you need for a vector, how much and which way.
All right, so we've got scalars and vectors. How does that actually apply to an object that's moving? Well, let's look at two words you've probably heard a million times, and maybe even used to mean the same thing: distance and displacement. I'm here to tell you, in physics, they are totally different. Let's imagine you're camping, right? You wander around and find an amazing fishing spot. You go back to your friend and say, "Hey, I found a great spot. It's 6 kilometers from here." Is your friend going to be able to find it? No way. They're going to ask, "Okay, 6 kilometers in what direction?" They need more than just a number. And this image right here shows you that exact difference. Let's say your tent is point A and the fishing spot is point B. You might have meandered along that winding, dashed path. The total length of that path, every step you took, that's the distance you walked. But your displacement? That's just the straight arrow, the most direct line from where you started to where you ended. So let's nail down these definitions. Distance is our scalar quantity. It only has magnitude. It's the total ground you covered. Think of it like the odometer in your car. It just keeps ticking up, counting every mile you drive, no matter if you're going in circles or in a straight line. It's just how much. Displacement, on the other hand, is our vector. It's all about your change in position. It doesn't care about the long, winding path you took. It only cares about the straight line from your start point to your end point, and the direction of that line. It's the ultimate shortcut. Okay, time for a quick pop quiz. Here's a classic example. A physics teacher walks 4 meters east, then 2 meters south, then 4 meters west, and to finish it off, 2 meters north. So first things first, what's the total distance she walked? Yeah, that part's easy, right? For distance, we just add everything up. You just take 4 plus 2 plus 4 plus 2, and you get a total distance of 12 meters. That's our scalar. That's the odometer reading of her little trip. But, and here's where it gets interesting, what was her displacement? Remember, for displacement, we don't care about the path. We only care about where she started versus where she ended. Her displacement is 0, a big fat 0. Think about it. She walked 4 meters east, but then she walked 4 meters west, bringing her right back to her starting east-west position. She walked 2 meters south, but then 2 meters north, bringing her right back to her starting north-south position. She ended her walk in the exact same spot she started, so her overall change in position was nothing. So now that you're an expert on distance versus displacement, we can take that exact same logic, that scalar versus vector idea, and apply it to another pair of words you use all the time: speed and velocity. You guessed it, one's a scalar and one's a vector. Okay, so speed is the scalar. It's how fast you're covering distance. Your speedometer says 60 miles per hour. That's a speed. It doesn't care which way you're going. Velocity, though, is our vector. It's the rate of change of your displacement. So it tells you not just how fast, but also in what direction. 60 miles per hour north. And here's the thing, that means if you're driving in a circle at a constant speed, your speed isn't changing, but your velocity is constantly changing because your direction is always changing. And now we can finally solve our puzzle from the beginning, the cross-country runner. They ran a distance of 10,000 meters, and I bet they had a pretty high average speed. But because they started and finished in the same exact spot, their total displacement was zero. And since average velocity is just displacement divided by time, their average velocity for the whole race was 0 meters per second. Wild, right?
So we're getting pretty good at describing motion, but there's one more layer to this. See, motion is always measured, well, relative to something else. And things get really interesting when the thing you're measuring against is also moving. This brings us to the cool idea of frames of reference.
Let's go back to an analogy. Imagine you're in a boat, rowing straight across a river. From your point of view in the boat, you're just moving across the water. But the river itself is flowing downstream. The water is moving relative to the shore. So your actual motion depends entirely on your frame of reference. Are you measuring it relative to the water or relative to a person standing on the riverbank?
So your total or true velocity is actually a combination of vectors. You have your rowing velocity, that's one vector, and the river has its own velocity, the current, that's a second vector. For someone on the shore to describe where you're going, they have to add those two vectors together. Your path won't be straight across, it'll be diagonal. It just goes to show all motion is relative. Now, I know this might all seem a little bit abstract, like it's just stuff for a physics test, but I promise you, understanding the difference between scalars and vectors, especially displacement and velocity, is absolutely essential for so much of the technology we rely on every single day. Think about a pilot trying to fly a plane. They can't just point the nose of the plane at their destination and hit the gas. They have to calculate the wind's velocity, both its speed and direction, and add that vector to their own plane's velocity to find out where they'll actually end up. Same thing for ships dealing with ocean currents. And the GPS in your phone or car, it's constantly using your velocity, not just your speed, to calculate the quickest route and give you that super accurate arrival time. So, I'll leave you with this final thought. If distance is the total number of steps on your fitness tracker, it's what your tired legs feel after a long hike, and displacement is that clean, straight line on a map that shows the shortcut back to your car, which one do you think matters more when you're lost in the woods and you're just trying to get home? Thanks for joining me.